In this example, we're going to be finding the third order Fourier approximation to the function 4t minus 6. Now, as a quick reminder, what a Fourier approximation is that if you have some sort of function, whatever it looks like, you can approximate it just by writing a bunch of factors of sine and cosine and adding it all up, plus some constant term. And so what we're going to be doing is writing this as an approximation using a constant and a bunch of sines and cosines. So first of all, I'm going to need to find the constant term, which is always over 2. If you go through the derivation of it, you get a null over 2. And this is going to be equal to the inner product of your function with 1 over 2 pi. Where the 2 pi comes from is that this is actually what the inner product of 1, 1 is. And in Fourier approximation, the inner product that we're using, this is part of what it means to do a Fourier approximation, but I'm just putting it up here, is that the product AB is the integral from 0 to 2 pi AB dt. So that's the inner product we're using when we're doing Fourier approximation. And if you do this integral with 1, 1, you just get 2 pi. So this is going to be equal to 1 over 2 pi times the integral from 0 to 2 pi of my function 4t minus 6 times 1. So I'll just write 4t minus 6 dt. Now if I carry out this integral, I get 1 over 2 pi times 2t squared minus 3t from 0 to 2 pi. I'm sorry, 6t. Shoop. Notice if I take the derivative of this, the 2 comes down. I now have 4t. If I have minus 6t, I take the derivative of that. I just get minus 6. So now if I plug in my values, I have 1 over 2 pi times 2 times 4 pi squared. If I plug in 2 pi and square it, I get 4 pi squared minus 6 times 2 pi. So this gives me 1 over 2 pi, 8 pi squared minus 12 pi. And finally, if I bring in this 1 over 2 pi, 8 over 2 is 4, pi squared over pi reduces to pi, minus 12 over 2 is minus 6, and the pi's cancel off. And so I have that a null over 2 is equal to 4 pi minus 6. So I know that in my Fourier approximation, I'm going to start with this right here. One moment as we speed up the video for me to erase this and do the next part. Now that we have determined the constant that's added on to the beginning of the Fourier approximation, we now need to figure out what the coefficients are going to be on our sine terms and on our cosine terms. It doesn't really matter which one I find first. I'm just going to do sine. So let me block that off. So now, I want to find the kth coefficient. We're going to do a third order Fourier approximation, so that means k is going to go 1, 2, and 3. A null we already found. A null or a sub 0 was the constant term that gets added on here. So now if I go to find ak, this is going to be the inner product of the function with cosine over cosine kt, cosine kt. And if you do this product, I'll still write it here. But in general, if you do the integral of cosine squared kt, you're going to get pi regardless of what k is. So this is 1 over pi. That's the bottom part, the cosine kt, times the integral 0 to 2 pi of our function 4t minus 6 with cosine times cosine of kt dt. Okay, let's get our integration muscles working. So I'm going to distribute the cosine in. So I've got 1 over pi integral from 0 to 2 pi 4t cosine kt minus 6 cosine kt. Okay, Now to integrate this right here, notice that it's a polynomial, 4t, times a trig function, cosine of kt. So we can take care of that by doing integration by parts. So I'll do that. And let me switch colors so we can keep track of everything. And this right here, the cosine kt, we're going to be able to split off on its own. In fact, let me go ahead and come over here so that I'll just write underneath here what my substitution is going to be. My substitution is going to be u equals 4t. So then du is 4 dt. My dv, for just this part here, is going to be cosine of kt times dt. So v is, well, the derivative of sine is positive cosine, so this is going to be a 1 over k sine of kt. Notice, because if you did that derivative by the chain rule, you'd have derivative of sine is cosine, and then the derivative of kt with respect to t is just k, so I need that 1 over k there to cancel that off. So if I now rewrite this over here, I have 1 over pi, bracket. This integral right here becomes uv, so 4t over k sine of kt minus u dv. So I'll put the 4 on the outside. So 4 integral from 0 to 2 pi uv, oh, v du. Whoops. Okay, so uv is 4t over k sine of kt, and the integral of v du. So this is 4 over k, integral of sine kt. So 4 over k, integral from 0 to 2 pi, sine of kt dt. And I need to be very careful not to forget this right here, minus 6 integral from 0 to 2 pi cosine kt dt. Close bracket. And this right here is evaluated from 0 to 2 pi as well. I'm just not writing all of those there because it's getting kind of cluttered. Okay. Woo! So now that I'm up to that point here, let's just go ahead and finish that integral. So the first part doesn't change. It's just 1 over pi integral 4t over k sine of kt. Now, integral of sine, well, it's going to be negative cosine because the derivative of cosine would be negative sine, so I need to offset that. So this becomes a plus, and I also need another 1 over k, so this becomes 4 over k squared cosine of kt. You can see that the derivative of cosine would be negative sine, which puts that negative there. And then by chain rule, I get a k, and so that would reduce with the k squared and just give me a k right here. Likewise, right here, this becomes minus 6 over k sine of kt. Again, take the derivative of sine, you get cosine, no sign change here, and then the k would cancel with that k right here. Notice that I have two like terms here, the sine kt, so I can put that together. This is all being evaluated from 0 to 2 pi. So I'll still do that over here, actually. So this is 1 over pi, 4t minus 6, all over k, sine of kt, plus 4 over k squared cosine of kt. Again, evaluated from 0 to 2 pi. Woo! Okay, so that was quite a bit. Let's go ahead and plug these in, and then we're going to have to think about what happens when the k is odd versus when the k is even. But first, I'm just going to plug in my bounds here as far as I can. And so if I plug these in, let me swap colors just so we can see that the integral is complete, and now we're evaluating. So 1 over pi is just hanging out here. If I plug in 2 pi here, I get 8 pi minus 6 over k sine of k times 2 pi. Don't forget that k, that's really important. Plus 4 over k squared cosine of k times 2 pi. Now if I plug in 0, let me save myself a little bit of space here. So I'm going to subtract these with 0 plugged in. Notice if I plug in 0 here, sine of 0, no matter what k is, whether k is odd, even, whatever, it's still going to be something times 0, which is 0, and sine of 0 is always 0. And then 0 times all this, it's 0. So I don't have to worry about that. The last one here, cosine of, again, anything times 0 will be 0. Cosine of 0 is just 1. So I have 4 over k squared times 1, or 4 over k squared. So this is minus 4 over k squared. Okay. Now, I need to think about whether or not k being odd or even makes a difference. So let's think about k being odd. Again, odd is like 1, 3, 5, etc., or -1, -3, -5. And let's think about what happens on the unit circle if k is odd for sine. Well, if k is odd for sine, then we have 2 pi, which is where sine is 0, if k was 1. If k was 3, we would have 6 pi, which is really just that position on the unit circle rotated around 3 times, which is still 0 for sine. Likewise, if I go in the negative direction. So if k is odd, this whole first term is going to be 0 every single time. Well, what about for cosine? Well, for cosine, if k is odd, we're always landing on 2 pi over and over and over again. And once again, we're at the same position, so cosine of that is 1. And so what do I get here? I get plus 4 over k squared times 1, which is 4 over k squared. But then notice I had a minus 4 over k squared right here. And so the whole thing comes out to be 0. So what does that tell me? Well, we were finding the coefficients for cosines, so at least for odd k, there will be no cosines, or in other words, the coefficients for them would be 0. What about when k is even? Now, if it helps you to think about it, remember that we're only doing a third order Fourier approximation, so you can just specifically think of 1, 2, and 3, because we're not going any higher than that. But keep in mind that if it was the nth order, we need to think in general about odd and even values. Let's think about when k is even, for our case 2. Well, if k was even, this would be 4 pi. Well, sine of 4 pi is still 0. And if this was even, this would be 4 pi. Cosine of 4 pi is still 1. So I still get the exact same situation. 0 plus 4 over k squared minus 4 over k squared comes out to 0. So all that work just to determine that all the coefficients for cosine are 0. That tends to be the way students kind of feel. They go like, really? I did all that for 0? Well, what if it was 1 or 7 or some other value, right? You did all that work because you didn't know what the number was. It happens to be 0. Okay, cool. Less room for mistakes, I suppose, when we write down our Fourier approximation. Okay, so we're in the home stretch. We've got the coefficients for cosine. In other words, there are no cosines. Now we need to find the coefficients for sine. So be right back while I clear up some room. Okay, so now that we know that this is 0 for all k, we can go ahead and find the coefficients for sine, which hopefully are not all 0. If they are, though, that just means our Fourier approximation is going to be 4 pi minus 6 and nothing else. But let's go ahead and find the sine coefficients. So it's the exact same as this, except instead of cosine, we're going to do it with sine. So let me call it b sub k now. So b sub k is our function using Fourier's inner product with sine of kt over sine of kt, sine of kt, which once again, this is pi. So I have 1 over pi times the integral from 0 to 2 pi of the function 4t minus 6 times sine of kt. Now to save me some writing space, let me go ahead and distribute that as I write it. So this is 4t times sine of kt minus 6 times sine of kt. Okay, now I need to do this integral. It's going to feel very similar to the one for cosine because sine and cosine are like that. They're derivatives of each other except for a sign error. Error if you mess it up. So first of all, this first thing right here, u is going to be 4t. So du is 4 dt. dv is sine of kt dt. And v is negative 1 over k cosine of kt. Again, derivative of cosine is negative sign. That gets rid of that. And then by chain rule, I'd have a factor of k there, which I need to cross off. Okay, awesome. So let me go ahead and do this integral. Look in here. 1 over pi bracket. So for this first part right here, we've got uv, so this is going to be negative 4t over k times cosine of kt minus the integral of v du, so minus a negative gives me plus 4 over k integral from 0 to 2 pi cosine of kt dt. And then, of course, minus the integral of 6 sine of kt, so minus the integral from 0 to 2 pi, oh yeah, minus 6 times the integral of 0 to 2 pi sine of kt dt, close bracket. Let's come over here. All right. So that doesn't change, negative 4 over t k cosine of kt. All right, integral of cosine of kt, that's going to be, let me leave the sign off, 4 over k. So this is going to be a positive sign. If I take the derivative of this, I would get cosine, and then a factor of k. So this down here becomes a k squared, so I can cancel that off. And then over here, integral of sine, that's going to be a negative cosine. So negative negative gives me a positive 6 over k cosine of kt, and all of this is evaluated from 0 to 2 pi. Again, notice how similar this is. I have two cosine terms, so I can combine these. So I'm going to have 1 over pi, parentheses, negative 4t plus 6 over k, cosine of kt plus 4 over k squared, sine of kt. Again, from 0 to 2 pi. And once again, let me plug in the values. I'll switch colors once again. We're done with integration. Now we're just evaluating the bounds. So if I plug in 2 pi, I've got 1 over pi. Negative 4 times 2 pi becomes negative 8 pi plus 6 over k. Put that in brackets. Cosine of k times 2 pi plus 4 over k squared sine of k times 2 pi. Again, let me try to save time with the 0. Minus, well, cosine of 0 is just 1, regardless of what k is. So this is just minus this with 0 plugged in. Well, negative 4 times 0 is just 0. So I just have minus 6 over k times 1, which is just minus 6 over k. And now minus this one, well, sine of some number k times 0, that's 0. So regardless of what k is, this whole thing just drops out and is 0. I'll still write it there, though. Okay. Now I need to think, does it make a difference on whether k is odd or even? Let's just think about k being odd. All right, if k is odd, we've got cosine starting at 2 pi. And if k is odd, we go 1 times 2 pi is 2 pi, 3 times 2 pi is 6 pi, etc. In general, because there's this 2 right here, it means that no matter what, whether I put an odd or an even number in here, it's getting multiplied by 2. So I will always get some even multiple of pi, which means that cosine is always hanging out at this location on the unit circle when k is odd, and let's just go ahead and go through that, when k is even as well. Cosine is still just hanging out in this section right here. So no matter what, cosine is always going to be 1, end of story. So for both of these, the first term is negative 8 pi plus 6 all over k, regardless of whether k is even or odd. Let's think about this one. Again, because it's the same thing inside the sign, the same argument applies. No matter what, this is always hanging out at 2 pi, which means it'll always be 0. So that just drops out. And so we have this minus 6k. And so we have that whether k is odd or even, this general form is going to give me the coefficients for my sine terms in my Fourier approximation. Give me one moment to erase this and make room, and then we'll finally write out the Fourier approximation. Okay, so now that that's all erased, I noticed here that down here I can actually simplify this just a little bit more. And so I'll do that right quick. Notice that this is a fraction, and so I can break this up into negative 8 pi over k plus 6 over k. And then I've got this minus 6 over k on the end here, so this actually drops off, which is really handy. The only other thing is that there was also a factor of 1 over pi outside the integral. So up here, the way I will write this down is I will just say that this is, remember, 1 over pi. And when we went through the integral, this comes out to just be negative 8 pi over k. And so these pi's are just going to drop off, and I'm going to have negative 8 over k for my coefficients on my sine terms. And so now we have everything we need to write the Fourier approximation. So let's do that now. The function f of t equals 4t minus 6 can be approximated by a third order Fourier approximation as 4 pi minus 6, that's my constant term at the beginning, plus, well, there are no cosine terms, so I'll put the plus 0 there just for emphasis. These are all the cosine terms, all 0. And then these right here, remember k is, this is a third order Fourier approximation, so k is going to go 1, 2, 3. So when k is 1, this is minus 8 over 1 times sine of 1 times t, which is just t. When k is 2, this is going to be minus 8 over 2, which is 4, sine of 2t. And when k is 3, this is going to be minus 8 over 3, sine of 3t. And there we go. Of course, on a test, you probably don't have to put the plus 0 there. I put it there for emphasis that we did go through the process of finding the coefficients for the cosine terms. It just so happened that they're all 0. So there we go. That is it. Remember, if this feels like a long process, you are watching a video that explains it, which makes everything feel longer than when you finally learn how to do it and you're able to just like go through it. Remember that this a null over 2, that's the way the form is set up, but you're actually adding a null over 2 at the start, so it's kind of a weird notational thing. Keep that in mind. And yeah, remember your integrals. That's this example.